So last class, we learned about significant figures. That was the last thing that we did. And we learned about significant figures because writing the correct number of numbers is important. And we'll get some more practice with that today in lab. However, it's not just significant figures. We also have to use significant figures in calculations. And so when we do that, when we use significant figures in calculations, the result, the final number, is rounded to reflect the significant figures of the data. So we do have to remember how to do rounding. And then there's two rules that we're going to learn for significant figures in calculations. If we have multiple steps, which we will often have, we will round only the final answer. For everything else, we'll keep all of the decimals, all of the digits that our calculator tells us. Every single one of them. To make sure that we don't end up with a rounding error. In labs, it's a little bit extra. We're going to oftentimes do a step. We'll ask for the number. We'll do a step. I'll ask for the number. We'll do another step. I'll ask for the number. And then finally, we arrive at the final number. For those, for labs, every number that goes into a data table should have the correct number of significant figures. So we'll put it into the table with the correct number of significant figures. And then if we use it again for another step, we're going to use the unrounded number. So if it goes into a table for reporting a value, we want the correct number of significant figures. When using calculations, we want to use the unrounded number wherever possible so that we don't have rounding errors. One of our two rules, one of our two circumstances, is multiplication and division. So we've got one rule for multiplication and division for significant figures. The result, the thing that we get from our multiplication and division, carries the same number of significant figures as the factor with the least significant figures, the least significant figures. So for multiplication and division, number of significant figures is what we care about. So a couple of examples with the numbers already crunched for us. We've got the number 5.02. This has 3 significant figures. We've got 2 non-zero numbers, and we have an interior 0, meaning it's between 2 non-zero numbers. Our second term has 5 significant figures. They're all non-zero numbers. Our third term and our final term has 2 significant figures. We've got a leading 0 that does not count. Leading zeros never count. And we've got a trailing 0 that's after a decimal point. A written decimal. And so this one is significant. So we've got 2 significant figures for that number. Which of our terms, what's the fewest number of significant figures that we have? 2, right? 2 is the smallest number. We've got 3, 5, and 2. 2 is what we are going to select. So that's the number of significant figures that we'll round to in our answer. So we count over from the left, 4, 5, that's our second significant figure. I denote the last significant figure by writing a line under it. This is especially helpful if we're going to be doing multiple steps. So this underline denotes the last significant figure, or is the last significant figure. And then we look at the next number to see how we round. We've got a 0, 0 is less than 5, and so we would round down or truncate, meaning we just drop everything after our last significant figure. So this turns into 45. In our division example, we've got a number with 4 non-zero numbers, so 4 significant figures. We've got a number with 2 non-zero numbers plus a trailing 0 after a written decimal point, so we've got 3 significant figures. Which of those is smaller, 3 or 4? 3. So we're going to go with 3 significant figures in our final answer. So we count over. 9, 6, 5 is our last significant figure. So we'll underline it. We're looking at the next number, the 9, to see how we round. 9 is 5 or greater, so we'll round up. So the 5 turns into a 6. So 0.966. Questions? As a reminder for rounding, I talked through it, but we've got it written out just in case you want to refer back to it later. We're going to only use the first digit being dropped. So the first drop digit, the first digit after our last significant figure, that's the only one that we're going to look at to decide how we're going to round. We round down / truncate. For or smaller. We round up for 5 and up. We're only going to round the final answer, except in labs where we'll round anything that goes into a data table. So examples, rounding these for 2 significant figures, 2.33. The 3 says that we round down. 2.37 rounds to 2.4. The 7 is 5 or greater, so it tells us we round up. Sometimes we'll have numbers like this one, 198.67. Our second significant figure is 9. The 8 tells us that we round up. This would round up to 200. However, only one of those zeros is significant, and so we need to put it in scientific notation. It needs scientific notation because otherwise we've got ambiguous trailing zeros. We want to avoid ambiguous trailing zeros. Another thing that I'd like to point out that we didn't do, because this will happen, somebody's going to do it at some point this semester, always happens. 198 is pretty close to 200. If we round it to 2 significant figures, we don't drop the 0 in the ones place, it doesn't turn into 20. It stays as approximately 200. So anytime that we round something, it should be about the same size, only changing it a tiny little bit. So numbers need to stay about the same size, because that will happen. Somebody will write, if we had this same instance show up, somebody would probably write 20. It shouldn't be 20, it should be 200. Little squiggle there, approximately. Need to stay at about the same size. All right, let's perform these calculations with the correct number of significant figures. First thing we can do, we can figure out how many significant figures we want for our final answer before we even plug it into our calculator. How many significant figures does our first number have? The 23.096. 5 significant figures. We've got 4 non-zero numbers, and we've got an interior 0. So that's 5. How about 90.300? How many sig figs? Also 5. So we've got 2 non-zero numbers, the 9 and the 3. We've got an interior 0. That's also significant. We've got trailing zeros with a written decimal point, so those are also significant. So we're going to expect how many significant figures for our final rounded answer? 5. So 23.096 times 90.3. Calculator says 2085.5688. Our fifth significant figure is the second 5. We look at the next number and only the next number to see how we round. It's a 6, which is 5 or greater, so we're going to round up. So this turns into 2085.6. Questions?
You have to put like the squiggle for approximate, or can you just put like equal to that number?
You can just turn it into the rounded number. Yeah. You don't have to write a little squiggle. All right, B, we've got 125 times 9.000. In our number 125, we've got 3 significant figures. In our number 9.000, we have 4 significant figures. When we're doing multiplication division, we care about the fewest number of significant figures. So we're going to expect 3 significant figures in our rounded answer. Plug this into our calculator. Calculator says 1,125. Our third significant figure is the 2. Look at the 5 to see how we round. Again, 5 is 5 or greater, so we are going to round up. So this turns into 113. Nope, we need a 0. 1130, so that it's about the same size. And then what do? We have to put it in scientific notation because we've got an ambiguous 0. It's trailing and we don't have a written decimal place. It's also not significant. So we would put this in scientific notation. We're going to move our decimal place over so that it's behind our first non-zero number. So our decimal part of our scientific notation, 1.13. And then we've got a times 10 raised to the, let's see how many places we moved our decimal place over. 1, 2, 3 spots, so times 10 to the 3. Questions about either of those? Yes?
For 125, why is it not like infinite sig figs since there's no decimal? Why is it 3?
So 125 is just 3 because it doesn't have units of like a countable number. So if it was like 125 students, then that would mean that it would have infinite significant figures, or if it was 125 nickels. But just the number, we would assume that it was just, we measured 125. Other questions? All right, our other set of rules, or our other rule set is for addition and subtraction. So we've got a rule for multiplication division. We've got another one for addition subtraction. For addition subtraction, we care about the number of decimal places. So instead of number of significant figures, it's number of decimal places. This is the one that will probably be a little bit confusing. I'll usually abbreviate decimal places as DP, just so you know it's not for Dr. Pepper, although we do love Dr. Pepper. Okay, so some examples. We've got the number 5.74. How many places after the decimal does this have?
2.
2 numbers after the decimal. How about 0.823?
3.
3. And 2.651?
3.
Also 3. So which of these is the fewest?
2.
2. So we'll expect 2 decimal places for our final answer, and that's where we'll round it. So when we do the addition, 5.74 plus 0.823 plus 2.651, 9.214. We're going to stop after the second decimal place, so this 1. We look at the 4 to see how we round. It's going to round down. So 9.21 would be our answer. For our second calculation or subtraction, 4.8 has 1 decimal place. One place after the decimal. 3.965 has 3 places after the decimal. 1 is smaller than 3, so we're going to expect 1 decimal place in our answer. Plug into the calculator, 4.8 minus 3.965. We get 0.835. Rounding for 1 decimal place, we look at the 8. That's our 1 significant figure in this case. The 3 tells us how we round. We're going to round down to 0.8. Final answer. The other thing that you can do for these, if you set them up with them stacked up for adding and subtracting, you can write a line through. So you could draw a line behind whichever has the fewest decimal places, and that's where you're going to cut it off. So to the left of the line, those are significant. To the right of the line, not significant. That'd be another way that you could do it. Questions about addition, subtraction? It does get a little funky if we've got something that doesn't have any places after the decimal. So I will sometimes just say, like, our last place is the ones place or the tens place or something instead of negative decimal places. We don't encounter that a lot. We usually have some decimal places. All right, we can also have these fun instances where we lose or gain significant figures when we're doing addition, subtraction, since we care about decimal places. So for example, we've got 2 numbers. They each have 2 decimal places. So we're going to expect 2 decimal places in our final answer. They also, not related to what we care about in this particular calculation, have 4 significant figures. When we do the subtraction, our calculator should tell us that this is 0.03. And that has how many significant figures?
2.
1. 1 significant figure. So this is something that will happen sometimes. This is normal. It's not anything to freak out about. It probably will happen to you in a lab, on a calculation, on a worksheet. So don't get freaked out by it. We can also have instances where we'll gain significant figures, and you'll probably see that happen as well. So that's normal, nothing weird. All right. Perform the calculations to the correct number of significant figures. I'll give you a chance to try these. So a minute or two, plug them in your calculator. See if you can figure out the correct number of significant figures. All right, when we're doing addition, subtraction, what do we care about? Number of decimal places. So we're looking at number of decimal places. 13.77 has 2 decimal places. 908.226 has 3 decimal places. So we're going to round our final answer to 2 decimal places. Our calculator tells us 921.996. Rounding that for 2 decimal places. Our second decimal place is our third 9. We look at the 6 to see how we round. We're going to round up. What's 1 bigger than 9? 10. So that last spot turns into a 0, and we add a 1 to the number to the left of it, which is a 9. So that turns into 10. And then we add 1 to the number to the left of it, which is a 1, so that turns into a 2. So this would round up to 922.00. This will happen occasionally where you have a 9 that has to round up. That's fine, that's normal. Just put a 0 in the place of the 9. We don't want to drop the spot that the 9 was in, though, because that's our last significant figure, our last decimal place that's important to us. So we need to make sure that we retain some zeros in those spots to keep track of our significant figures. And then for B, I put that in wrong. We have 0 decimal places, 0 decimal places, and 2 decimal places. 0 is smaller than 2, so we'll expect 0, got distracted by Siri. We have 0 decimal places for our answer. The number is 2001.06. 0 decimal places means we would be rounding after the ones place. So this would turn into 2001. Questions about either of those? So 2 different rules. We've got multiplication, division. We care about the fewest number of significant figures. Addition, subtraction. Here we care about the fewest number of decimal places. Individually, independently, not confusing. However, we will sometimes do both. Maybe alternating between the 2, doing one at a time. Maybe we've got them both plugged into the same thing. And this is where people usually get confused, because we have to work one step at a time. We also get to remember PEMDAS. Parentheses, exponents, multiplication, division, addition, subtraction. This is our order of operation. So anything that's in parentheses, we're going to do that first, no matter what it is. Then if we have exponents, we'll do the exponents next. Then we would do multiplication, division. Then we would do addition, subtraction. And every step, we have to assess either number of significant figures or number of decimal places. We have to be keeping track at each step along the way. And then we'll round the final answer. So let's see some examples of this. Ah, yes, this slide. I've got parentheses in here to separate things that we're multiplying. So step A, number A, letter A. Like I said, brain's fried. Letter A, we've got 2 times 1.008 grams. What are we doing operation-wise? Parentheses, we just have a number in parentheses. So we're going to be doing multiplication. This is our first step. So we've got multiplication. We also have the addition. Multiplication comes first. So 2 times 1.008. How many significant figures does the number 2 have? One significant figure. 4 significant figures in our 1.008 grams. Cool. I'm just remembering where that number came from. So that should be infinite sig figs. We won't worry about it. User error. So plug that into our calculator. We get 2.016 grams. Since the 2 has one significant figure, what would be our last significant figure in the number 2.016?
The 1.
The 2. If we have got one significant figure,
Oh.
only the 2 is significant. How fun. And then, what do we do after our multiplication? Addition. So we're going to add the 15.99 grams. This number, 2.016 grams, has how many decimal places that are significant? The 2.016. How many significant decimal places does it have? 0. It has 0 because it has one significant figure. Only the 2 is significant. The rest of the numbers we're just keeping on to make sure that we don't do a rounding error. So the 0.16, not significant. So if we were to count this for decimal places, sorry, not 1, 0 decimal places. 15.99 has how many? 2 decimal places. So the smaller of those is 0. So we'd add those together. $18.006 units of grams. The 8 is our last significant figure. So this would round to 18 grams. Are we seeing how this could be confusing? Once we get some practice, once you learn the rules of the game, it won't be confusing. Hopefully we can learn the rules. Questions about that example? All right, then we've got B, 137.3 seconds plus 2 times 35.45 seconds. What are we doing first? Multiplying. So 2 times 35.45. Let's assume that the 2 is exact. It doesn't say that here, but let's just assume that it is, because I think one of these was supposed to have an exact 2. If that's an exact 2, how many significant figures does it have?
1.
Infinite, which basically just means ignore the significant figures. We don't have to consider it for that number. So this one's infinite sig figs. 35.45 has how many significant figures? 4. So if we've got 4 significant figures and infinite significant figures, which one of those is smaller? 4. So plug in 35.45 to your calculator. See what our intermediate number is. What did we get? 70.9 is what I heard. How many significant figures does that have? 3. How many are we supposed to have? 4. How would we get this? How would we add a significant figure to that number? We'd add a 0 to the end. So that would make it 4 significant figures. So if you're ever in need of another significant figure, this will often happen if you're adding, subtracting, multiplying, dividing. Anytime you've got a trailing 0 after the decimal place, your calculator will drop it. So this is what I would call your calculator betraying you. We know that there's supposed to be a significant figure there. We need to remember that there's supposed to be a significant figure there, so we need to add it back in. Okay, so we've kept it 4 significant figures. And now we're doing addition. What do we care about for addition? Number of decimal places. So I'll rewrite this over to the side. $137.3 has how many decimal places? 1. 70.90 has how many? 2. Because they're both significant. So the smaller of those is 1. So we want to round, if we need to 1 decimal place. So into our calculator, 137.3 plus 70.90. Calculator says 208.2. For 1 decimal place, we'd underline our 2. After that would be a 0. 0 says round down, so our calculator has helped us. It already dropped the 0 for us. Final answer? $208.2? Seconds. We're just missing the unit, that's all. But yes, 208.2 would be our final number. All right, for C, our italic C example, again, we'll assume that this 2 is exact. So that'll have infinite sig figs. What's the first operation that we're doing? Addition, subtraction, multiplication, or division? Divide. We've got 118.7 grams divided by 2. When we're doing division, we care about number of significant figures. So we've got 4 significant figures and unlimited significant figures, so we're going to have 4 significant figures for our intermediate. So 118.7 divide by 2, 59.35 grams. It's already 4 significant figures, so nothing to do there. And then we subtract 35.5 grams. When we're subtracting, what do we care about? Decimal places. So 59.35 has 4 significant figures. Now we care about decimal places. It's got 2 decimal places. 35.5 has only 1 decimal place. 1's the smaller of those. So we're going to round our answer for 1 decimal place. So 59.35 minus 35.5, we get 23.85 units of grams. We want to round that for 1 decimal place. So our 8 is our last significant figure. Next number is a 5. 5 tells us we round up. So this is 23.9 grams. Questions? Great. So that's significant figures. We will use them for the duration of the course. So you do have to know how to use them, especially in labs. We'll just kind of mention them occasionally when we're doing calculations. All right, chemistry has a lot of problem solving in it. It's part of why it's confusing. There's also a lot of like really weird details. Another reason that it's confusing. So with problem solving, sometimes we'll have to get to an equation to solve, and usually we'll be given a problem statement. Sometimes it's a word problem. Word problems tend to give people trouble. They won't always be word problems, but there is a certain amount of skill in taking a problem, taking a question text, and figuring out what are we actually answering. So I'll try to talk through like how we're finding what we're looking for, what's important information, what's not. When we get to problems, it is a skill. So we're not going to have any simple formulas that apply to every single problem. There will be a couple of formulas, a couple of solution maps that we do that will show up time and time again, which is great. We can also learn some problem-solving strategies. I'll talk about some of those. Many of our problems can be thought of as unit conversion problems. We'll be learning about unit conversions soon. Sometimes we'll also require the use of specific equations. There's like, depending on how you count them, there's maybe like 12 equations. So it's not like a crazy amount of equations. I don't think they're particularly difficult. Usually it's just you plug stuff into your calculator. So converting between units. We can treat our units like any algebraic quantity. Algebraic quantities being things like x, y, and z. Any of our units, all of our units behave this way. So one approach to solving problems is just looking at the units, and we call this dimensional analysis. So looking at the dimensions, analyzing the dimensions being things like length, width, height, time, any sort of unit. Dimensional just refers to units. So crucial to doing dimensional analysis, crucial to doing unit conversions, we need to write every number with its unit. Always write units every single time. Every intermediate, every conversion factor, anywhere that a unit is supposed to be, make sure that you write the unit out. I will be doing that for the entire duration of the class in all of our examples. I'll always be writing our units unless I just want to see if we remembered. I don't need to, personally. I'd be perfectly fine just plugging this stuff into my calculator and hitting enter, doing it to show you that we need to write the units. You can sometimes save a problem that you might have screwed up if we write our units in. We also want to make sure that they don't magically appear or disappear in our calculations. So we want to treat them like variables in algebra. So x over x, x is the same as x. Whatever x is, doesn't matter, it will turn into 1. So we can get rid of things in algebra by dividing by them, and we can make them appear by multiplying. And we'll probably see some examples of that, but my brain is, again, fried. For most of our unit conversion problems, we'll have a few today, we'll be given something with some units and be asked to convert to another unit. So we'll be starting with some units, we'll be asked to convert to another unit. And typically, these calculations are going to be pretty simple. We'll be given some information. For example, maybe we're given 5.5 centimeters, and we want to convert this to inches. We would need to find a conversion factor. We'll talk about how to make conversion factors. We would need to find something that converts from centimeters to inches. Our conversion factor should have the units that we have and the units that we want in it. So the conversion factor that we would be using in this case would have 1 inch on the top and 2.54 centimeters on the bottom. The 2.54 centimeters on the bottom means that we're dividing by 2.54 centimeters. Since we've got a centimeters on the top and a centimeters on the bottom, those will cancel out just like the x over x that we saw before. It turns into a 1, so we can just poof, get rid of it. And what units do we have left? Inches. And so inches would be the unit that carries through. So if we did 5.5 divided by 2.54, we would end up with a number of inches. It would be about 2.2. We can make conversion factors from any two things that are equal. This is a table that shows some units that we can convert between. So for example, ounces, the unit of weight, not the unit of volume, and grams, we can convert between those two. 1 ounce is equal to 28.35 grams. We can also convert between fluid ounce, apparently. Fluid ounce, that's the volume form of the ounce, and milliliters, and lots of other things. There's lots of ways that we can convert between different things. And we can find them in a table. We can also do it with stuff that we just know off the top of our head. The more that you use these conversion factors, some of them will stick and you'll just memorize them, which is super helpful. I'm also having some reference sheets printed out that'll have some conversion factors on them that I'll hand out. Hopefully I'll have them for next class. So to construct a conversion factor, we need the two things that are equal. How many feet are in an inch, or how many inches are in a foot? 12 inches equals 1 foot. There's two conversion factor forms that we can make with this. And the way that we do it is we want feet and inches to both be on one side. So the way that we would move something with algebra is we just need to make sure that we're treating both sides equally. So let's say we want to move the inches over to the feet side. 12 inches is what we're going to divide both sides by. That will get rid of the 12 inches on the left. 12 inches over 12 inches, that's equal to 1. And then on the other side, we've got 1 foot over 12 inches, and that would be our conversion factor. So one of our conversion factors, 1 foot over 12 inches. There's another form of the conversion factor. The other form is just what divided by the other thing. So 12 inches is equal to 1 foot. If we divide both sides by 1 foot, the right side turns into 1. 1 foot divided by 1 foot. Those are the same. So that's a 1. And then the other side would be 12 inches over 1 foot. What do we notice about those two conversion factors? They're inverses. We've just flipped the top and the bottom. That's the shortcut for coming up with the other conversion factor. So you can flip the top and bottom, the numerator, the denominator, of a conversion factor. Just make sure that you flip everything. The reason that we can flip them and the reason that we can use them in the first place is because when we were constructing the conversion factor, we divided both sides, on this case that I'm talking about, by 1 foot. So this right side turned into a 1. And if you take the inverse of 1, it's also 1. So you can flip the top and the bottom, because this is equal to 1. And we can also multiply by this number, the 12 inches over 1 foot. We can multiply that by that without changing anything because it's equal to 1. And anytime you multiply by 1, nothing changes. It's the same thing. That's the trick, the maths behind why conversion factors work. For inches and centimeters, 1 inch is equal to 2.54 centimeters. So there's also 2 conversion factors that we can make with these 2 things that are equal to each other. One of them we would get by dividing both sides by 2.54 centimeters. The shortcut for moving things for dividing or multiplying both sides, if it's on the top on one side, you can move it to the bottom on the other side. If it's on the bottom on one side, you can move it to the top on the other side. So one of our conversion factors would be 1 inch over 2.54 centimeters. The other conversion factor is going to be the inverse, or the flip the top and the bottom of that, 2.54 centimeters over 1 inch. If you're comfortable doing that algebra in your head, and you know that you're not going to screw it up without dividing or multiplying both sides, you're welcome to just do it. You don't have to show me that you did it. If you're not 100% sure that you can do it without messing something up, then I encourage you to write it out until you get comfortable with it. Questions? So one of our skills, one of our important skills that we need to know how to do for this class is to be able to make these conversion factors from any 2 things that are equal. It will show up multiple times. Okay, so for unit conversions, when we're solving problems, we want to make sure that the final units are correct. For these, we need to make sure that the units cancel. If we don't actually cancel out our units, if we don't do we've got 1 on the top, 1 on the bottom, so those cancel out, it's possible that you put in the conversion factor, you put in the inverse, the flipped one. So then you actually multiplied instead of dividing. Let's look at what that looks like. So for example, if we're trying to convert, let's say that we forgot to put our units in. If we tried to convert inches to centimeters, and we did this, 2 times 1 divided by 2.54. We left off the units that go with the 1 and the 2.54. So we'd do 2 divided by 2.54, we'd get some number. The units that are supposed to be with the 1 and the 2.54 are inches and centimeters. So with the units in there, we can see we've got inches on the top twice. So the inches multiply, get inches squared, over centimeters. So this wouldn't be centimeters, be inches squared per centimeter. Does that mean anything to anyone? Inches squared per centimeter? Doesn't mean anything to me. I forget what I call those. I've called them crazy people units before, but maybe a little bit insensitive. Nonsense units. Doesn't mean anything to anyone. We did the calculation upside down. So our conversion factor is flipped. What we would actually want to do is have the 2.54 centimeters on the top, the 1 inch on the bottom, and then the inches cancel and it turns our units into centimeters like we had intended. So just an example of getting things flipped. We also want to make sure that the magnitude, if we can tell, the magnitude, the size of our answer makes sense. So for example, if I wanted to convert my height from feet to meters, I'll embellish a little bit and say that I'm 6 feet tall. So let's say that I'm 6 feet tall just to make the conversion easy. If I'm converting 6 feet to meters and I come up with 19.8 meters, does that seem right? Am I 20 meters tall? I'm definitely not 20 meters tall, right? I could get away with saying that I'm 6 feet tall, maybe. But 20 meters tall, no chance. So seeing that I got 20 meters, I must have screwed up my calculation. That would be an example of checking the magnitude. So the issue was, for going from 6 to 19.8, I multiplied by 3.3 instead of dividing by 3.3, which would be like a rough conversion. It would actually be like maybe 1.8 meters tall. That's more believable, right? A meter being about 3 feet. Kind of in the right ballpark. For a lot of the problems, you won't have a good sense of whether our magnitude or our size is correct. I will try to point out some things that I'm thinking about when I'm thinking about magnitude problems. For a lot of these issues, we can just invert our conversion factors, so flip the top and the bottom. So that can be a really easy way to fix some issues. When we are converting between units, when we're solving any problem really, we often may benefit from having a solution map. This will give us a visual outline. I usually focus on units. That shows the path we're going to take, the steps that we're going to take to solve the problem. So one multiplication or division at a time. Again, typically we can focus on the units. For now, they're going to feel a little silly because we're going to be doing 1 or 2 step problems. Later in the class, we will frequently be doing things that have 3 or 4 steps. So it can be really helpful to map out our problem ahead of time and think what units can we switch between. And it'll save us a lot of time. So as an example, a solution map for one step for converting from inches to centimeters. We would write out inches on the left, centimeters on the right. We can do this in one step. This is our conversion factor. So we've set it up from inches to centimeters. Our conversion factor has inches on the bottom, so that'll cancel out with the inches that we started with. The centimeters is on the top, and so that will be our final answer. The solution map for the other direction, from centimeters to inches, is the same, just flip them. So centimeters on the left, inches on the right. I usually use green to indicate something that we're given or something that we can start with, and I'll use the pink or fuchsia to indicate what we're trying to find or what we're trying to get to. And then we can do that conversion in one step. This time we've got, in our conversion factor, we've got centimeters on the bottom. That'll cancel out with the centimeters we started with. The inches that are on the top will carry through, and those will be our new units. So generally, we can identify a starting point or given information. We can identify the endpoint, what we need to find. What we need to find is usually next to a question word. Not always, but usually. Can anyone give me an example of a question word? A question word?
What?
A question word.
My answer was what?
Yeah, what would be an example of a question word? Any other examples? Anyone?
Like how many?
How? Yeah, just out loud would be great.
Oh, how?
Yeah,
Oh, like how many?
I'm doing the bit again.
Oh, okay.
So how would be another example? Thank you. Who would also be another example. So who, what, when, where, why, how, all of those words. Any of the words that you would typically end a sentence with a question mark because you're using that word, those are our question words. So who, what, when, where, why, how, etc. Those would all be some question words, not exclusively. There could be other things. We won't always have a question. We'll also sometimes just be told, do this thing. And then we can do the solution mapping part. So we'll start with what's given on the left side, what we're trying to get to on the right side, and then a number of steps, one or more, to get there. And that would be the solution map that we come up with. And this just says the same thing, but we've baked it all into the first two steps. Once we've got our solution map, we can write everything out, do the math, think about our significant figures, cancel units, and then check things. Does it make sense? Does the magnitude, does the size seem okay? Are the units correct? If we don't have the correct units, we don't have the right answer. And is the number of significant figures correct? So for example, convert 56.0 centimeters to inches. A lot of the time things that we're given have numbers with them. So 56.0 centimeters is what we're given. We're trying to get that to inches. Our solution map, we're starting with centimeters. We're trying to get to inches. Can we do that in one step? We sure can. We'll need something, a conversion factor that has centimeters in it and inches in it. So we could find 1 inch equal to 2.54 centimeters. And we would need to make the conversion factor to go from centimeters to inches. Since we have centimeters, we want the centimeters part to be on the bottom. So we would divide both sides. We would end up with 1 inch over 2.54 centimeters. For setting up the problem to solve 56.0 centimeters, and then when I do multiple steps, I usually write one big long line that separates the numerator and the denominator, the top and the bottom. And then I'll use vertical lines to separate the different things. So 1 inch over 2.54 centimeters. And I made this line too long, so we'll shorten it. This is the same as writing 56.0 centimeters and our conversion factor after it. These are the same. I usually write the top one, partly because if you tend to, do a little bit of accidental up and down with your writing and you don't keep everything nice and straight, having that line between your numerator and denominator can be helpful. Okay, let's check our units. We've got centimeters, one on top, one on the bottom. So those will cancel out. The units that are left over are inches. Inches is what we want. So assuming we didn't get our inches switched, or our units switched in our conversion factor, this should be correct. 56 divided by 2.54. Calculator says 22.047. But wait, there's more. 24409. Is that our final answer? No, it's not. What do we need to do? Sig figs. How many significant figures should we have? We look at our 56.0. It's 3 significant figures. Our conversion factor, secretly infinite sig figs. It's an exact conversion. So we would round for 3 significant figures, which turns into 22.0 inches. Box it in, final answer. Questions? All right, one for you to try. Convert 1,342 meters to kilometers. The kilo prefix is equal to 1,000. All right. So, solution map. We're starting with meters, trying to get to kilometers. We can do this in one step. We would need to know a conversion between kilometers and meters. Kilometers, km, has the prefix, meters doesn't. So we'll set 1 kilometer equal to how many meters? It's 1,000. So this k equals 1,000. So we can plug in the 1,000 where that k goes. So then this would be 1,000 meters. The other way that you could figure it out, a meter, about 3 feet. A kilometer, not exactly a mile, but it's kind of like on the same ballpark, 4 laps around the track, kind of a long distance. No, that would be a mile, sorry. It would be 1,600 meters. But big unit. So 1 kilometer, much bigger than a meter, 1,000 meters. We're going from meters to kilometers. So we would want the kilometers part to be on the top. That's the unit we want to end up with. We also need to cancel out the meters. So we want the 1,000 meters on the bottom. So 1 km over 1,000 m would be our conversion factor. So 1,342 meters multiplied by our conversion factor. We've got meters on top, meters on the bottom. Those will cancel out. No more meters, just kilometers. So kilometers comes through. Perfect. That's the units we wanted. And then dividing by 1,000, this turns into 1.342 kilometers. Questions? We can also have multi-step unit conversion problems. We'll probably have these show up quite a bit. It's the same procedure, but more steps. So we can determine a solution map and then follow it to solve the problem. We've still got 2 minutes, so hang with me. So an example, converting 194 centimeters to feet. We're starting with centimeters, going to feet. Can we do that in one step?
No.
Probably not, at least not with the things that we would think of for conversions. Is there something that we can convert centimeters to? Yeah, we could convert centimeters to inches. Can we convert inches to feet?
Yeah.
We sure can. And then underneath each of our arrows, we'd want to put in what our conversion factors are. So we need something that relates centimeters and inches. We need something that relates inches and feet. 2.54 centimeters equals 1 inch. 12 inches equals 1 foot. We want to make sure that we get the correct form. We're starting with centimeters, so we want the centimeters to be on the bottom. That'll make sure that they disappear. So 1 inch over 2.54 centimeters. Then we would have inches. We want to make sure the inches disappear, so we get the 12 inches on the bottom, 1 foot on the top. So 1 foot over 12 inches. Those would be our 2 steps. And then we can write out what the calculation looks like. So put some numbers in. 194 centimeters. Our first conversion factor, 1 inch over 2.54 centimeters. Centimeters on the top, centimeters on the bottom, those will cancel. And we would have units of inches left, which is where we want to be in our conversion. We're following our solution map. We're on track. Our second step, 1 foot over 12 inches. We've got 1 inch on top. We've got an inch on the bottom. So those will cancel out, turn into a 1. The units that are left are feet, which is where we're trying to get, so that is perfect. So then we would put into our calculator 194 divided by 2.54, also divided by 12. It'd be 6.36 feet after we round for 3 sig figs. So we can do 194 over 2.54 also over 12. That'll get you the right answer. Or you can do 194 divided by, and then do 2.54 times 12 in parentheses. Those will both get you the correct answer on your calculator. Questions? Okay, we'll finish chapter 1 next class.